Hi, everyone, and thank you so much for joining us today, and welcome to the October edition of the Conservation Outcomes webinar series. My name is Elizabeth Creech, and I am a Natural Resources Communication Specialist with the USDA Natural Resources Conservation Service, Resource Inventory and Assessment Division. It's great to be here with you all today. We host this webinar series to highlight activities across the Natural Resources Conservation Service, or NRCS, related to efforts to assess and quantify the impacts associated with NRCS conservation programs. We will get started with today's presentation in just a moment, but first, a few logistics. If you would like to receive email notifications with information on upcoming webinars, please subscribe to the NRCS Conservation Outcomes topic via GovDelivery. You may do so by following the instructions on the screen. The sign-up link, along with all other resources from today's webinar, is available on our new NRCS Conservation Outcomes webpage. You may access that by visiting nrcs.usda.gov/conservation-outcomes-webinar. And I'll say that one more time and then a few times later. That's nrcs.usda.gov/conservation-outcomes-webinar. This is the webpage where most participants likely joined with today's event, so thank you. On the screen, you will see how to access live captions during this webinar by clicking the three dots with the word More at the top of your screen. This will enable you to select the Turn on Live Captions function. All participants are currently in listen-only mode, and all audio is being broadcast through your device's speakers. If you are having problems with audio, sometimes computer or mobile device headsets can help with the audio quality and volume. It may also help to unjoin, then rejoin this Microsoft Teams webinar session. We hope you'll have questions as you listen to today's presentation. If so, please hold on to those and we'll have time for a Q&A session at the end. At that time, we'll ask you to use the raise hand functionality as shown on the screen, and we'll help you unmute your microphone. You may also email my colleague, Amy Overstreet, with any questions we don't address today. Her email address, as shown on the screen, is amy.overstreet@usda.gov. Amy's email address is also located at the bottom of the Conservation Outcomes webinar webpage. Please note that we've posted additional resources online, including a PDF of today's PowerPoint presentation and references, and a one-pager of associated resources related to this content. You can access that, you probably already guessed it, at nrcs.usda.gov/conservation-outcomes-webinar. And with that, enough from me. It's time to get started. I'm pleased to turn the microphone over to Dr. Mark Hsu, Director of NRCS's Resource Inventory and Assessment Division.
Welcome to the latest installment of NRCS's Conservation Outcomes webinar series. As you know, NRCS has a long history of working with farmers and ranchers to help them conserve the natural heritage and sustainability of their operations. Those recurring webinars give us a way to communicate to our stakeholders the importance of voluntary conservation programs and the funding provided through the Farm Bill for those efforts, and to highlight some of the documented outcomes in terms of natural resource and economic benefits. For nearly 20 years, our Conservation Effects Assessment Project, or CEAP, has been documenting outcomes of our work on a variety of resource concerns. Today, we will hear more on the work under our CEAP watershed assessment studies. Those projects work closely with science partners in other agencies, universities, and with farmers to document and understand outcomes that help inform improved conservation delivery across the agency. Today's webinar is well-timed with NRCS's recent outreach campaign on smart nutrient management. This is an effort to help farmers implement smart activity to reduce nutrient loss through comprehensive assessment of site-specific conditions. Today, Dr. Kevin King of ARS will share with us details about the science that supports water quality outcomes that can be achieved through smart nutrient and water management strategies. I appreciate you all being with us today, and at this time, I'd like to turn it over to Lisa Durancic, NRCS SEEP Watersheds Assessment Leader, to introduce Dr. King. Lisa.
Hi, good afternoon, everyone, and thanks for joining our webinar today. We're really pleased today to have Dr. Kevin King with us to share some of his research. Dr. King is a research leader and supervisory ag research engineer with the USDA Agricultural Research Service at the Soil Drainage Research Unit, which is located in Columbus, Ohio. He's an internationally recognized authority on edge of field and watershed scale water quality data collection techniques and determining hydrologic and water quality responses of conservation implementation in tile-drained landscapes. His research unit is a member of the USDA SEEP project, as well as USDA's long-term agroecosystems research network. And they conduct research to advance sustainable agricultural production and protect water resources in artificially drained landscapes. He's leading and collaborating multiple projects aimed at quantifying edge-of-field water quality effects of agricultural production and conservation management practices in the Eastern Corn Belt. Currently, his work is focused on identifying production and conservation practices that can reduce phosphorus movement to Lake Erie, as well as to inland water bodies. So I'd like to turn it over to Kevin at this time, and thanks for joining and for sharing with us today, Kevin. Okay, we can see your slides, Kevin. I think you're muted.
I apologize, I was muted. So first of all, thank you, Lisa and NRCS, for the invitation and opportunity to speak with you today regarding an important conservation topic, specifically addressing water quality concerns through nutrient and water management. The research and science that I will cover today is a contribution of several of my colleagues as well as my own research. It is a part and product of the Conservation Effects Assessment Project, specifically the watershed assessment studies. I should also note that many, but not all of the examples that I will give are related to phosphorus, as my primary research and the resource concern in the Western Lake Erie Basin watershed is phosphorus. So with that, let's get started. Nutrient transport is a product of both the nutrient source, whether it be organic animal manures or inorganic commercial fertilizers, and transport mechanisms. That is excess water leaving the field, whether it's by surface runoff or subsurface tile drainage. If there is no transport mechanism, then off-site nutrient transport should not be a concern. The nitrogen and/or phosphorus used for crop production will be used by the crop or remain in place. Think in terms of a zero discharge system. Let's dive into the source component a little more deeply. Nutrient source inputs may be internal and external. Internal sources are primarily associated with nitrogen and include fixation associated with legume crops. Whereas external nutrient sources include commercial fertilizers and organic animal manures. In the left-hand illustration from the USDA ERS, we can see that fertilizer use has increased since the 1960s, but somewhat plateaued in more recent times. Regardless, there are a lot of commercial nutrients that have been applied in the agricultural landscape and a lot that still remain in the soil. This left-hand graphic illustrates only the commercial or synthetic fertilizer usage. The right-hand graphic is representative of organic materials. The data here also come from the Economic Research Service and begins in 1986. But you can also see an upward trend and a somewhat of a plateau associated with the organic fertilizer sources as well. Where there exist animal operations, the organic manures offer another source of fertilizer. And given the current cost of commercial fertilizers, organic sources will no doubt be utilized if available. In the Western Lake Erie Basin watershed, where most of my research is located, organic sources account for approximately 20% of the annual fertilizer source, with the remainder being synthetic or commercial blends. Switching to the transport side of the equation, volume and intensities of rainfall events are changing. We see more extreme events in terms of rainfall, volume, and intensities, and those increases are often in the spring when producers are trying to be in the field to plant crops. The national average for increased annual precipitation volume is 4%. In Ohio, that is 5 to 15%. Over the last several years, we have witnessed significant increases in the number of 2+ inch rainfall events, and that number is only expected to rise. From the period of record, 1895 through 2019, at this point, 8 of the top 10 wettest years occurred since 1990, and 6 of the top wettest years have occurred since 2004. In the Eastern Corn Belt region, we are definitely seeing shifts in both the volume and intensities of rainfall events. Alone, neither source or transport pose a water quality risk. However, the agricultural systems that we deal in are not zero discharge systems. They are leaky. And because they are leaky, there exists a risk of off-site transport and downstream issues. Here I have used the algal bloom issue in the Western Lake Erie Basin to illustrate risk. However, you can pick your resource concern, whether nitrogen related, for example, the hypoxia zone in the Gulf of Mexico, sediment, or some other agrochemical, for example, pesticides in drinking water supplies. Regardless, the risk associated with any of these issues is proportional to the overlap or magnitude of the source and transport mechanisms. To better understand the interaction of source and transport mechanisms, we can look at data from the Western Lake Erie Basin, ARS Edge of Field Network here in Ohio. Using discharge and water quality data from roughly 8,000 rainfall events across 40+ privately owned and operated crop production farms, we've shown that 80% of the nitrogen and phosphorus loading and runoff occurs during 10 days per year, while 80% of the nitrogen and phosphorus loading in the tile drainage occurs during 45 days per year. Similarly, and looking at this from a precipitation standpoint, we can see that approximately 60% of the surface phosphorus loss and 40% of the subsurface tile loss, phosphorus loss, originates from the top 20% of precipitation events. Here, that top 20% of events is approximately equal to 1¼ inches of rainfall. As rainfall volumes and intensities increase, this transport problem will only be exacerbated. Thus the need for both nutrient management and water management. So now we're going to dive into the meat of the presentation. The 4R Nutrient Stewardship Initiative, that is, the right source of fertilizer applied at the right rate, in the right place, and at the right time, was started by the International Plant Nutrition Institute and the Fertilizer Institute to promote the 4R program across North America. There was a large initiative in the Western Lake Erie Basin that was supported by the agricultural community. Within the Western Lake Erie Basin, nearly 2 million acres are managed under the 4R initiative through agreements with certified crop advisors and/or fertilizer co-ops. These institutions are voluntarily audited every 3 years and have to meet a 40+ point criteria for certification. Similarly, NRCS recently released the SMART initiative, the Source, Method, Assessment, Rate, and Timing, which is founded upon the same science and core principles of the 4R initiative, with the addition of an assessment component. Most of this is also housed in the NRCS 590 standard for nutrient management. The next part of this presentation is to dive a little deeper into each of the factors, the source, the method, the rate, and the time, to understand some of the science that supports the program, and look a little more closely at those site-specific characteristics which go into the assessment component of SMART. We will also discuss ways to manage water, because as previously noted, source alone is generally not an issue. Finally, we will discuss the need for additional practices and approaches, as the 4Rs, or SMART, generally addresses only acute losses. That being said, smart nutrient management should be the minimum goal for every producer. Source is concerned with matching fertilizer type and availability to crop needs. When considering nutrient source, availability is one issue. As previously noted, the current cost of commercial fertilizer can present a challenge. If organic sources are available, producers will most likely take advantage of that opportunity if they have a way to transport and apply the nutrient. Everything else being equal, nutrient solubility should be considered. The solubility of organic and inorganic sources varies. Inorganic fertilizers are generally more soluble than organic sources, at least initially. To illustrate this point, a study in Iowa applied equal rates of P2O5 phosphate from beef manure, poultry litter, liquid swine manure, and commercial fertilizer. They did a rainfall simulation on the plots within 24 hours of application and determined that the greater losses of phosphorus came from the commercial fertilizer sources compared to the organic sources. However, the continued use of organic sources tends to increase soil test phosphorus concentrations, as well as phosphorus concentrations in the discharge. Indeed, a study of 39 agricultural fields in Nova Scotia, Canada, revealed that the long-term use of organics tended to increase soil test phosphorus in those fields, and the phosphorus concentrations over time were greater from poultry and swine manure sites compared to the commercial sites and sites using only dairy manure. Within the tile drain landscape of the Eastern Corn Belt, there are a few studies that have directly compared organic and inorganic sources. We have ongoing research to investigate nutrient losses from commercial and organic sources. Preliminary findings suggest that manures applied at equal P rates to inorganic sources tend to slightly increase tile drainage dissolved reactive phosphorus loads. However, the increases were generally small and on the order of grams per year from the liquid dairy manure site compared to the commercial site. So think back to the previous slide. Initial losses may be greater from commercial sources, but over time, the losses are near equal. Similarly, we have two additional studies within the Edge of Field network where we are exploring the use of commercial fertilizer compared to swine manure and poultry litter. In both cases, we see similar low magnitude increases in dissolved reactive phosphorus loss with the use of swine manure and poultry litter. Taken collectively with the liquid dairy manure study previously highlighted, we can say that the use of organic sources, when applied at equal P rates to commercial sources, creates a slight increased potential in dissolved reactive phosphorus loss to tile drainage at the field scale, but these upward trends were not statistically significant in all cases. However, when accumulated over the watershed scale, these minute losses could manifest into a larger issue. Furthermore, It should be noted that these studies are on one set of paired fields and warrant further investigation across a gradient of soil types, background soil test phosphorus levels, drainage intensity, and crop production management. Now we will turn our attention to fertilizer rate. The land-grant universities have recommendations for fertilizer rate based on soil test levels. This generic graphic illustrates the three areas of fertilizer application as they relate to rate, specifically phosphorus. First is the critical level. Below this level, we would expect to see a yield response to fertilizer application. The middle zone is the maintenance level. Here, we would not expect to see a crop response to added fertilizer. Finally, the final zone is when we have soil test levels that exceed the maintenance limit. If soil test phosphorus concentrations are in this level, there is no need to apply fertilizer. However, up to a certain level, it is permissible and state dependent, and is generally a result of having organic sources and limited storage. For further information concerning application when soil test concentrations are above the maintenance limits, please visit your respective state's 590 standard. Within the Western Lake Erie Basin, several farmer surveys have taken place over the last few years. Based on a 2013 survey data and responses from greater than 2,200 Ohio farm fields, 90% of those fields have crop rotation phosphorus application rates at or below recommended levels. Crop rotations here are generally characterized as corn-soybean or corn-soybean wheat rotation. For the rotation, 905 of the 2,200 fields had crop rotation phosphorus application rates at or below recommendations, while 58% of the fields had zero phosphorus applied. This data suggests that the majority of producers do adhere to application recommendations. Using soil test data and water quality data from the 42 fields within our Ohio Edge of Field network, there is clear evidence that soil test phosphorus concentrations above the agronomic levels generally poses an environmental risk. However, soil test phosphorus levels above the agronomic level does not necessarily equal environmental risk. We have several instances where concentrations exceed that maintenance limit, but we still don't see a response from water quality, a negative response. Similarly, and using data from multiple peer-reviewed research studies across the United States, it has been documented that as phosphorus application increases, so does phosphorus loss. In Iowa, and with more respect to nitrogen, at the watershed scale studies indicate that the late spring nitrate test predicts available nitrogen and reduces nitrogen loss. Nitrate nitrogen loss was reduced by 30% using the late spring nitrate test and did not have an effect on corn yield. Thus, soil testing and adhering to recommended rates reduces the potential for nutrient loss. We will now turn our attention to method. When we think about method or placement, we generally talk about surface broadcast versus subsurface placement approaches. Here, we will explore the effects of these two methods on stratification and water quality from field scale to plot scale studies. Surface broadcast applications lead to stratification. Dr. Dave Baker and colleagues from Heidelberg University collected data cores from 232 different soil locations across the Sandusky River watershed, a sub-watershed of the Western Lake Erie Basin. They found significant phosphorus stratification. That is, soil test phosphorus concentrations that were 2 to 3 times greater in the top inch of soil compared to concentrations down to 8 inches. Broadcast application without incorporation leads to stratification and increased losses. Similarly, Dr. Mark Williams, using data from one of our Edge of Field sites within the Edge of Field network, showed that a shallow disc of approximately 3 inches, so incorporation of about 1.5 inches following application, significantly reduced concentrations and losses in the tile drainage. Within a day of tilling one field and not the other after application, an approximate 1-inch rainfall occurred. When we compared concentrations coming from the tile drainage, we saw a 5 times greater increase from the surface broadcast site compared to the site that was tilled. Likewise, the actual amount of loss was 7 times greater from the surface broadcast application compared to the tilled field. So the message is that we need to get the nutrients below the surface. However, we are not advocating wholesale tillage. We are suggesting that the use of subsurface placement tools or light incorporation. The results are very compelling in terms of subsurface placement. Similar to that study, but at a different edge of field site, we compared broadcasting fertilizer without incorporation compared to a more aggressive tillage, that is, a tillage with a disc chisel. Using 2.5 years of baseline data and 2 years of treatment data, preliminary analysis indicate a significant increase in the dissolved reactive phosphorus from the broadcast application compared to the incorporation site. In contrast, total phosphorus, that is the phosphorus that is associated with the sediment, in the tile drainage decreased with the broadcasting and was a result of less soil disturbance, which brings up the question of trade-offs and unintended consequences and understanding flow pathways and water management. However, that is a totally different topic which should be explored during another webinar. With respect to manure and using data out of the Chesapeake Bay area, placement was also shown to be very important, as significantly less losses occur with incorporation when compared to broadcast only. Similar to the field scale studies, plot scale studies reveal the importance of subsurface placement. Using a lysimeter approach and rainfall simulation, it has been shown that concentrations in the leachate water were significantly greater from broadcast application without incorporation compared to leachate concentrations which were injected or tilled in. Similarly, a 3+ year plot scale study in Ohio investigated the effects of different placement methods that included surface broadcast plus disc, 2x2 placement at planting, and a deep placement 3 to 5 inches below the row. In general, the fertilizer that was placed below the surface had less losses compared to the broadcast. The deep placement treatment had consistently less losses compared to the broadcast until the last month of the study. The fertilizer was applied in early December, and over the following 3 days, rains totaling roughly 2.5 inches fell, increasing the losses even though they were placed 3+ inches below the surface. This observation makes the case and stresses the importance of timing just as much as placement. Indeed, fertilizer application followed by rainfall creates the potential for large incidental phosphorus losses. Unpublished data from Heidelberg University on the Honey Creek watershed within the Western Lake Erie Basin shows a strong correlation between application and subsequent losses over a 3-month period. Thus, when applying fertilizer, it is important to be cognizant of the forecasted weather and make decisions accordingly. Using a unique data set of approximately 7,000 precipitation events observed across 40 agricultural fields within the Western Lake Erie Basin network, a multiple regression analysis using 29 controls of precipitation event-driven discharge, nitrate load, and dissolved reactive phosphorus load from subsurface drains showed that prolonging the period between application and rainfall had a decreasing effect for both nitrogen and phosphorus. Results showed that both tile nitrogen and phosphorus loads were positively influenced by transport and source variables, including event discharge and total fertilizer applied. One of the factors that showed a negative or reducing effect for both phosphorus and nitrogen was time since application. In addition to the watershed and field scale studies highlighted here, there are several rainfall simulation studies that also confirm decreased nutrient loss with delayed rainfall after application. Furthermore, There are several tools and apps available for producers to look at site-specific forecast and base their decisions accordingly. In addition to time since application to first rainfall, the time component of SMART also includes time of year. Applications closer in proximity to crop needs tends to have less loss. Data out of the Ohio demonstration farms showed that in-crop manure applications reduced nitrate loads and marginally increased phosphorus loads. This study is a part of a collaborative effort between NRCS, the Ohio Farm Bureau Federation, and the Ag Research Service. These results are based on 3 years of data from a paired design, where we had baseline data for a period and then implemented the in-crop treatment. Comparing water quality parameters between the fall manure and UAN application showed a small increase in phosphorus loss. The biggest benefit was realized in the nitrogen component. The in-crop manure treatment reduced annual nitrate losses by 9.4 pounds per acre. In studies out of Iowa and some of my own research here in Ohio, it is also clear that application in winter and before precipitation significantly increases the risk of loss. Further, some preliminary data from the Ohio Edgefield Network shows that spring manure applications resulted in less loss compared to fall applications. This data was analyzed using a before-after control impact design and study with 4 years of data, 2 years of pre-treatment data, and 2 years of post-treatment data. Collectively, these studies indicate that applications closer in proximity to crop needs tend to have less loss. Anytime a crop production change is made, a reassessment of nutrient management needs to be conducted. In-season assessment as it relates to nutrient management would also be beneficial and might include tests such as the cornstalk nitrate test and late spring nitrate test. Additionally, there are several tools and apps that are available to identify field-specific risk, including phosphorus indices and the soil vulnerability index, to name a couple. In addition to field and in-crop assessments, site-specific and regional concerns should also be considered and may include soil quality, legacy sources and hotspots or variable source areas, a changing climate, and producer capabilities, to name a few. Now let's look at each of these in a little bit more detail. One of the first site-specific assessments that should be made is an investigation of the soil quality. Poor soil quality alters natural flow paths that short circuits matrix and natural soil filtering and can potentially negate any efforts associated with the SMART aspects in the initiative. Poor soil quality can reduce infiltration, leading to increased surface runoff. Poor soil quality, especially as it relates to soil structure, can enhance desiccation cracking and preferential flow and represents a direct flow path to tile drainage. Poor soil quality and preferential flow pose a difficulty in implementing the SMRT aspects and assessing the benefits, specifically as they relate to the source, placement, and timing. Another assessment topic is variable source areas. Variable source areas, or hotspots, if hydrologically connected, can disproportionately contribute to field loss. These variable source areas, or hotspots, are often characterized by nutrient concentrations that far exceed agronomic levels. They are often referred to as legacy sites and may be reflective of old animal barns or feedlots that have long been demolished. Legacy sites can serve as a chronic source of nutrients for years and decades and mask effects of current conservation efforts. As we think about management options, these legacy areas or fields will require different conservation management than what is offered in SMART. While SMART should still be practiced, there should be an understanding that additional conservation management practices will need to be implemented. Site-specific assessment should also include a socioeconomic analysis. Producer resources, specifically time and money, think here about access to equipment and the time involved to implement. Think broadcast versus subsurface placement. are often cited as concerns for not adopting conservation practices. In multiple surveys of producers within the Western Lake Erie Basin and led by researchers at Ohio State University, a majority of the farming population is willing to consider many of the recommended conservation practices and approaches. However, they point to conservation practice efficacy, whether it is real or perceived, as well as the financial and time burden often associated with some of the recommended practices as barriers to adoption. To overcome some of these barriers, farmers will need better cost-benefit information, site-specific decision support tools, and technical assistance, including outreach and education, workshops, and field days, in order to more rapidly adopt and execute the placement of smart practices, as well as other recommended conservation. We've already touched on this with respect to the transport mechanism. However, the changes in climate should also be considered in that assessment part of SMART. Specifically, changes in precipitation amounts, intensities, and timing may make parts of the SMRT aspect implementation a challenge. We all know that the windows of opportunity for field activities are getting smaller, especially given our larger equipment and the wetter conditions. Even though we plan on implementing SMRT parts of SMART, local weather conditions may complicate a producer's ability to carry out the plan. Thus, we need to also consider how water management can be used to disrupt hydrologic pathways and reduce nutrient loss. Water management can reduce hydrologic connectivity and improve water quality. Water management practices include, but are not limited to, drainage water management, also known as controlled drainage, retention-detention basins that can later provide irrigation water, blind inlets, wetlands, cover crops, and newer practices such as cascading waterways. Controlled drainage, NRCS Standard 554, also known as drainage water management, is the practice of artificially raising the outlet elevation of field-scale tile drainage, thus promoting in-field water storage. Several studies across the globe have investigated the agronomic as well as the water quality benefits of controlled drainage. Controlled drainage has been shown to significantly reduce drainage volume, that is, the amount of water leaving the field as tile drainage. On an annual basis, this reduction is generally in the range of 30 to 40%. Likewise, controlled drainage significantly reduces nitrate-nitrogen loss in tile drainage in that same 30 to 40% range. However, with respect to phosphorus, the results have been mixed. Some studies show increasing, decreasing, or no effects of drainage water management. Further, the implementation of drainage water management may increase surface discharge and associated surface loss of nutrients, especially in the winter and early spring. However, these increases should not negate the overall benefits realized with controlled drainage. From an agronomic perspective, the practice has the potential to increase crop yield as there is still potential water that the crop could use. However, this increase generally occurs every 2 to 3 or 4 years rather than every year. Blind inlets disrupt surface flow to tile drainage and filter surface runoff. In the pothole or surface depression topographies, surface inlets are often installed to more rapidly remove surface waters that would otherwise pond in the depression. By removing surface inlet and replacing it with a blind inlet, we slow down the movement of water and promote siltation. The water is still allowed to leave but a slower rate and a rate that will not cause root damage. This water management practice, NRCS Practice Standard 620, disconnects the surface discharge contribution, thus reducing the sediment and sediment-bound nutrients entering the tile systems. Conversion to a blind inlet has been shown to reduce sediment up to 70%. Results with nitrogen have been variable and not surprising since we generally do not associate nitrogen movement with surface waters. Phosphorus reductions have been shown to be reduced by approximately 50%. To further enhance the system, the gravel layer can be replaced with a phosphorus sorption material and further reduce the dissolved fraction of phosphorus leaving the site. Wetlands have potential to reduce moderate discharge rates and become nutrient sinks. Research has shown wetlands to be a good mitigation approach for both nitrogen and phosphorus. However, wetlands are limited in addressing larger discharge rates and have a limited lifetime before transitioning from a sink to a source. This is especially true for phosphorus and is dependent on the concentration and load being delivered to the wetland. The typical lifetime with moderate phosphorus loads is 10 to 15 years. However, regular monitoring needs to occur to know when the transition from a sink to a source occurs. Further, wetland adoption has been minimal unless it has been positioned in marginal lands because producers are hesitant to take land out of production. That being said, wetlands do have an environmental benefit and should be considered a water management practices as well as a water quality practice. Another drainage water management approach that is gaining some traction is the concept of drainage water recycling. Drainage water recycling is an approach to move toward a zero discharge system. Drainage water recycling is based on capturing most or all of the drainage water for later irrigation. This practice or management approach increases crop production as water is generally available for irrigating during times when otherwise there would be limited water or only water that was delivered through precipitation. Because this is a near zero discharge system, there would be significant reductions in both nitrogen and phosphorus to downstream waters. Additionally, this system offers potential benefits for flood control and can serve as wildlife habitat. It may not be as direct as controlled drainage, retention-detention bonds, or blind inlets, but cover crops have the potential to alter the field-scale hydrology and nutrient delivery. Cover crops alter field-scale hydrology through increased evapotranspiration and promotion of infiltration, thus disconnecting the hydrologic pathways. Past research has shown that cover crops can reduce surface runoff by upwards of 2 inches while increasing tile drainage. But cover crops also increase evapotranspiration. Work from our Edge of Field Research Network shows that the water balance in cover crop fields is altered by increasing evapotranspiration from 4 to 16%, while decreasing discharge 16 to 30%, with the remainder of that water being stored in the soil profile or biomass. The use of cover crops on a field-by-field basis also resulted in significantly less nitrogen loss, while results associated with phosphorus were mixed. That is, some studies showed increasing losses from cover crops, while others showed decreasing effects or no effects. Thus, understanding the resource concern and identifying an appropriate practice is critical for addressing water quality concerns. As we have previously indicated, nutrient management is focused on the acute losses or those losses associated with recent fertilizer applications. Additionally, we are dealing with leaky systems and have also made a case for different water management practices. Regardless, nutrient and water management may not be enough to address the issues. Thus, we need to be thinking broader in terms of the entire system that includes stacking, in-field and edge-of-field practices, as well as structural practices placed at the edge of field or in the drainage ditch. These practices include, but are not exclusive to, phosphorus removal structures, denitrifying bioreactors, saturated buffers, or drainage ditch design and management. Phosphorus removal structures, NRCS practice standard 782, are designed and implemented to target high phosphorus loss sites. They can be used to address surface runoff or subsurface drainage and are generally more effective when phosphorus concentrations are greater. Typical designs seek to reduce total phosphorus loads by 40% over a 3 to 5 year period. Software exists to facilitate the design of these structures. For more information regarding phosphorus removal structures, look at NRCS Standard 782 and reference the book highlighted here, or reach out to Dr. Chad Penn with Ag Research Service in West Lafayette, Indiana, who is the developer and expert on this practice. Similar to phosphorus removal structures, denitrification bioreactors target nitrogen losses. Denitrification bioreactors are generally located at the edge of field near a drainage outlet, but other installations have been constructed, for example, in a grassed waterway. Edge of field structures are generally designed to affect an area of 50 to 80 acres, but that can be site and field specific and also depend on drainage design. They roughly have a footprint of 25 by 75 feet and are generally 4 to 5 feet deep. But again, that is dependent upon site-specific characteristics, including the drainage area and target load reduction. Most are filled with wood chips, but other carbon sources have been explored. Nitrogen removal is dependent on discharge rate, with typical reductions in the 20 to 30% range. Research is still ongoing and to enhance these bioreactors, especially during cold climates. This is a cost-shared practice, and further information can be found in the NRCS Standard 605. Drainage ditch design and management has the potential to create nutrient sinks. There are over 14,000 miles of agricultural drainage ditches in the Western Lake Erie Basin watershed. This provides a lot of opportunity to affect a change in discharge and water quality. One method that has received a lot of attention is the idea of ditch design, specifically the construction of two-stage ditches. More information can be found in NRCS Standard 582 for open channels. This practice is generally implemented when there is a bank stability issue and there is evidence of sloughing and bank erosion. With this practice, the ditch is widened to create a floodplain, allowing greater flows to spill over onto the floodplain, promote interaction with the floodplain vegetation, and create an opportunity for nutrient assimilation and removal. Studies have shown this design to have reducing effects for sediment transport as well as nitrogen and phosphorus. In Mississippi, the idea of vegetative drainage ditches or linear wetlands have been explored and shown to reduce phosphorus in the growing season by upwards of 60%. Stacking or combining practices has the potential to further reduce nutrient loss. Stacking may include 2 or more in-field, edge-of-field, or in-stream practices. Benefits may not be 100% additive, but should provide additional reductions in targeted nutrient losses. Several studies are underway to gain a better understanding of stacking practices. This graphic is from one of our fields in Ohio, where we are investigating multiple practices that include in-field management, edge-of-field practices, things like controlled drainage and phosphorus removal structures, as well as ditch design, specifically the two-stage ditch design. As part of my wrap-up, I would like to share a graphic that I think summarizes not just SMART, but our entire conservation effort and questions that we still need to address. In this graphic, which is hypothetical, but based on our experiences and current research, we can see that we get the most benefit from upland or infield practices, specifically those practices related to SMART, as I have outlined and discussed today. As we move up in scale to the edge of field and in-stream ditch practices, the effectiveness tends to decrease, and this is primarily related to our practices' inability to handle large discharge rates. Other questions that we should be asking are, how do we avoid trade-offs and unintended consequences as we focus on a specific nutrient? Should our practices change based on the ecoregion where we work? And what timescale should we expect to see an environmental response? There is a lot of inertia built up, and changing the current direction and trends may take longer than anticipated. This is not a reason to give up. It should be the motivation to work at getting more conservation in the landscape. In summary, and with respect to the source part of SMART, solubility varies between organic and inorganic sources. When applied at equal rates, potential for slight increases in phosphorus loads have been measured. The method part of SMART should focus on subsurface placement, as placement below the surface significantly reduces loss potential. Not every farm, field, or producer is the same. Thus, site-specific field characteristics and socioeconomic conditions need to be considered in the assessment part of SMART. The R in SMART, or rate, should focus on soil testing and, at a minimum, adherence to land-grant university guidelines. Applying rates consistent with crop requirements or less reduces nutrient loss. The final component of SMART focuses on time. Awareness of local weather forecast and applications closer to crop utilization generally reduce loss potential. Because we are operating in leaky systems, we also need to have a water management plan. Water management is just as important as nutrient management. Finally, we understand the SMART and water management alone may not be enough to address certain water quality issues. Thus, stacking practices and implementing other edge of field and in-stream practices may be necessary to meet nutrient reduction goals. With that, I thank you for your time, and I will answer questions if there are any.
Thank you very much, Kevin. That was a really great presentation and very thorough overview. And I do want to make sure to point out again to folks that there are some additional resources available on that outcomes webinar page in case you joined us a few minutes late and didn't hear that at the beginning. So go to that page afterwards to download those resources that Kevin and we compiled. So we'll go to a few questions now. And I see Sandy Bin has her hand up. And Sandy, if you can go ahead and unmute yourself, or we'll do that for you, and you can ask your question of Kevin, please.
Thank you very much. So my first question is, in the beginning of the presentation, it was limited to poultry manure and swine manure. What about an assessment of dairy manure? And I guess I'll just ask these, and then Kevin, I have like 3 or 4 questions. I'll just ask them together, and then maybe you can respond. Of the 40 fields that you're looking at, how many of those fields that you're tracking are using manure, and what kind of manure are they using? Liquid, swine, dairy, poultry? And the last question is with regard to changes in volumes. As we get more and more animals in the Western Lake Erie watershed, the shift of putting more and more manure in the ground is happening. And how do you, in terms of economic incentives or getting reductions in how much manure is going to be applied compared to fertilizer that does have an economic component if it's not needed, how do we deal with the management of manure compared to the management of fertilizer, both of which are different?
Yeah, so let me answer your, let's see, I think you asked 3 questions or 4 there. Let me try to get the first one. The first one had to do with, is anybody looking at dairy manure? And you may have missed that, but yes, we have a study, and matter of fact, that manuscript is getting ready to be submitted for publication consideration right now. So we have on our Edge of Field network studies going on where we're looking at dairy manure, swine manure, and poultry litter. With respect to all of those, there were slight, like I said, grams per year increases in the dissolved phosphorus losses coming from the manures compared to the commercial fertilizers. On a field by field basis, that's not a large concern. They're pretty much equal. The concern is if, as you mentioned in I think one of your questions here, if we get more and more, how does that manifest itself at the watershed scale? And I guess, Sandy, the answer is I don't know. You know, I think we have the NRCS 590 standard. There's guidelines on those in terms of recommendations and with application. I think it's something that we have to keep an eye on. At this point, the 20% of the fertilizer right now that is being used in the Western Lake Erie Basin is from manures. That number, could probably go up to 40, 50% and not do anything at all with respect to increased loading significantly. That's just a gut feeling. But it's something we need to keep an eye on, as you point out, and I pointed out. The commercial fertilizer costs are getting to a point where farmers are going to try to utilize these organic sources. So it's something we need to be aware of. Then your other question was, how many do we have within our network? Out of the 40 fields, about a third to a half of them use organics as their primary source of nutrients. Of those, probably half to 2/3 is liquid dairy manure. And the other ones are swine manure. We don't really have poultry in the mix right now. We had some brought in for specific to facilitate a study, but that's sort of the makeup of our network.
Thanks, Kevin. We do have another question from Michelle Perez. So Michelle, we'll go ahead and unmute you and you can ask your question, please.
Thank you. That was a terrific presentation. Thank you so much, Dr. King. This is honestly not a gotcha question. It might be hard to answer, but I'm wondering if you have a gut feeling or you know specifically how the practices you emphasized in your presentation today do or do not dovetail with the practices called for or prioritized in the Climate Smart Commodity Program projects. And so what kind of an opportunity do we have upon us as those 70 and then plus projects, start implementing their priority practices to address these many water quality concerns? Is it a great overlap? Is it a minor overlap? Do you have a sense for that?
I honestly have no idea. I'm aware of the program, but I have not investigated it to be able to tell you what that overlap is. One thing that concerns me, which is probably related to this as a researcher, is a lot of our practices are designed for current day conditions, and we're not looking at these practices as we think about rainfall or intensities that are increasing. And grant we have droughts in some areas, but as these are in the humid areas where we're located, we don't necessarily think about how these practices are going to function when we get twice as much rainfall or half as much rainfall. And I think we need to be thinking in the future about new practices or how to make these practices more resilient to those types of climates. But to answer your specific question, no, I don't know.
Thank you, Michelle. Great question. We can look into that some more and I'll see if I can get you more of an answer afterwards as well. Are there any other questions from any attendees? And if not, I'm going to go ahead and turn it back over to Elizabeth Creech to wrap us up today. We have one more. Do we have time, Creech, or?
Could we maybe take this one by email? Make sure we share our final slides with everyone.
Yep, and go ahead and give that email address again so that we can get that question. Thank you.
Yes, of course. So just a few final remarks and we will share our resources. First and foremost, a huge thank you, Dr. King, for sharing your presentation and insights today. Also a big thank you to Dr. Shu, Lisa Duranchek, and my behind the scenes communications colleague, Amy Overstreet. So before we go into today's resources, we want to briefly provide details on our next Conservation Outcomes webinar, which is scheduled for December 8th at 1 p.m. This webinar will feature University of Nebraska-Lincoln's Dr. Dirac Twidwell presenting on sustaining forage production by reducing woody encroachment in the Great Plains. Information for that webinar too will be available on our webinars page. And then as a reminder, resources from today's webinar are currently posted on the Conservation Outcomes webinar webpage. One more time, that URL is nrcs.usda.gov/conservation-outcomes-webinar. We encourage you to visit if you haven't already. There you can access a PDF of Dr. King's presentation with citations, a one-page document with additional resources, a recording of today's webinar, which we'll post by next week, the sign-up link for Conservation Outcomes webinar notifications, all packaged in our recordings and resources, and our contact email addresses. As Lisa, you just flagged, those are available at the bottom of that webpage. We hope to see you again for future Conservation Outcomes webinars. Have a great afternoon, everyone. Truly, thank you so much for joining us. Bye-bye.